All right, so today we're going to talk about ideal gases. And as you probably already know, there is an ideal gas law called, which the equation is PV equals nRT. And it's essentially a model about how gases behave, and it's a relationship between the pressure of the gas, which has to be reported in absolute pressure, the volume of the gas, the number of moles of the gas, and the temperature of the gas, which also has to be in an absolute temperature scale. So examples of absolute temperature scales are degrees Rankine and Kelvin. And we have this famous little constant called the ideal gas law constant, which gives a relationship between pressure, volume, and temperature of an ideal gas. So what is an ideal gas? There is no actual gas that's completely ideal. So it's a model for how gases behave. And the model works best when the following assumptions are close to being true. It assumes that the molecules do not occupy space. So it's very important to understand when you're using a model what assumptions the model is based on, because then you can determine, if you know what the model is based on and when it performs the best, it's easier to decide when it's something that you can use and when you need to use a better model. So we are going to be using the ideal gas law, so you have to be able to justify why it's a good assumption or not. The second assumption, that there are no attractive forces between gases, the gas molecules, and that the collisions between the molecules are perfectly elastic. So one question you want to ask yourself is, when are these assumptions most accurate, particularly with respect to the parameters in the ideal gas law? So when pressure is low, you don't have very many molecules, so they're not likely to interact very much. And when the temperature is high, it's also going to be unlikely that the molecules, or less likely that they'll be able to influence each other very much through attractive forces. So the question is, what is low? And it depends on your tolerance in terms of how accurate you want the model to be. But if you want it to be within 1% or so of the actual gas behavior, you're probably pretty safe if the pressure is less than, let's say, 3 atmospheres, and if the temperature is greater than 200 Kelvin. So our physiological conditions meet those criteria, so that's why we can use the ideal gas law as often as we're going to. So I'm going to go to the next page here, and I'm going to explain a way to use the ideal gas law called the ratio method, which in essence eliminates the need to use the gas law constant. So I just turned on the voice recorder. I can use that to replace the sound if this isn't good enough. It would be a good experiment. So if you take, you can kind of, it's a way to explain why the ratio method works. We can write out something using the ideal gas law, where you say PV equals nRT, but I'm putting a little subscript A in here to indicate that we're talking about actual conditions. that the gas is under in terms of pressure, temperature, volume, moles. And we're going to compare it to standard conditions. And, hopefully you know by now that standard conditions are that the temperature is 273 Kelvin and the pressure is 1 atmosphere. And when that is the situation, and you have an ideal gas, the ideal gas occupies 22.4 liters per gram mole. Or another way of saying that in a different unit system is it occupies 359 cubic feet per pound mole. So these are things that you should remember, those numbers, so you can use the ratio method. Remember these. That way you won't have to remember the ideal, or even use the ideal gas law constant ever again. So, if you look at these equations, and suppose you're given temperature and pressure of a gas, and the problem, you want to find out the number of moles there are of this gas. Well, if you go up here and look at these equations, well, first of all, R is going to be the same for each. Standard pressure, standard volume in moles. You see these numbers right here are actually V over N. So we know what V over N is, and we know what standard temperature is, and you're given the pressure and the temperature of the gas. So how do you find the volume? Well, you can rearrange this equation that I just showed you, and you could say, well, the number of moles is equal to the actual pressure over the standard pressure times the actual volume over the standard volume times the standard temperature over the actual temperature, and all of that times the number of moles at standard conditions. And you can actually rearrange this one more time so that you isolate the number of moles at standard condition divided by the volume at standard conditions. That we know is equal to 1 gram mole occupies 22.4 liters. That's the number that I said you need to memorize. So you'll always know that and have that in your hip pocket. And then we rearrange this equation above. So you can think of this as what you're really doing is you're correcting the fact that if it's an ideal gas at standard conditions, 1 gram mole occupies 22.4 liters. You're correcting the fact that you're not at standard temperature and pressure. That's what this part of the equation is doing. So what you're doing is you're essentially calculating what the actual moles per volume is for this gas. So you can figure out how many moles you got if you know the volume. That's what the ratiometric method is doing for you. So let's do an example problem. Suppose you have a mixer and you have gas coming in that's at 50 degrees and 50 atmospheres, and it's composed of carbon dioxide, and it's coming at 100 liters per minute. Suppose you're mixing that with air that's at 25 degrees C in 1 atmosphere, and you have 50 liters per minute. And the question is, we'll call this the feed stream, this will be the air stream, and this is the product stream. So the question is, if the product stream is coming out at 1 atmosphere and 25 degrees C, what is the volumetric flow rate of the product stream? Now, some people might be tempted to say, oh, well, it's 150 liters per minute because you got 100 liters per minute coming in of CO2, and you have 50 liters per minute of air coming in, right? Not right. The reason is volume is not conserved. Please remember that. Now, truth is, if you're mixing liquids, for the most part, volume will be roughly conserved, except in a few rare situations. But with the gases, it's not going to be the case at all, because volume is not really conserved. By what I mean is, if you mix 2 liquids, 1 liter of one kind of liquid and half a liter of another, the final volume is going to be close to 1.5 liters. That's not normally the case with gases at all. So the first step here is you want to convert volume or volumetric flow rates to something that is conserved. I mean, they're conserved as long as there's no chemical reactions. And even if there are chemical reactions, you know how to account for the change in moles using the extent of reaction. So we want to get to a place where we can use an accounting equation or a conservation equation. And so volume, that's not going to be useful. You can't do that with volume. So we want to get things into moles. So that's where the ideal gas law comes into play. So one question we may want to do is figure out is how many moles of CO2 are in F, the feed stream. So here's where the ratio method comes in. Okay, we got 100 liters per minute coming in, and we want to turn that into moles. So what I'd like to do is start with, we know what the relationship is between volume and moles for an ideal gas in standard conditions. So we can start with that, and we want the units to balance out. So we know that there's 22.4 liters per gram mole at standard conditions. Now we want to correct for the fact that we're not at standard conditions, okay? The carbon dioxide that's coming in the feed stream is at 50 degrees Celsius, and standard conditions is 0 degrees Celsius. So, the fact that it's warmer than standard conditions, if you remember, will tend, as you warm up a gas, it occupies more volume. So what you can do is think, well, if an ideal gas at standard condition, if 1 gram mole of an ideal gas at standard condition occupies 22.4 liters, then if it's warmer, it'll occupy more volume. So we want to multiply a ratio of the actual temperature to the standard temperature. And since we know that the relationship between volume and moles should go up, that the temperature is warmer than standard, we can very quickly realize that the standard temperature needs to go in the numerator, actual temperature in the denominator. This corrects for non-standard temperature. Now we want to correct for non-standard pressure. as the pressure goes up, you would expect the gas to occupy less volume. So we want to put the ratio of actual pressure to standard pressure in such a way that it'll cause the volume occupied. It'll correct the 22.4 liters per gram mole to make the volume smaller than 22.4 liters. So the numbers that we're talking about are 50 atmospheres. That's what it's coming in at, and the standard pressure is 1 atmosphere. So to make the relationship here between volume and moles smaller, we would have to put 50, the actual pressure, in the numerator and the standard pressure in the denominator. And that's it. You now can solve for what the actual moles per volume are for this gas. And it turns out to be 188.6 gram moles per minute CO2 in stream F. Okay, so now we're going to go ahead and figure out the moles of air. So if I were you trying to learn how to do this, I would stop this screencast right now and try to figure out myself, see if I can do it first and then see how I do it. Okay, so here's what we have coming into the air. We have 50 liters per minute. And we know that if it were an ideal gas at standard conditions, 1 gram mole would occupy 22.4 liters. Now, if you were to multiply these two out, you'd have moles per minute, but that would only be true if the air is coming in at standard conditions. But it's not, so we need to correct for the fact that it's not. It's coming a little bit warmer. It's coming in at 25 degrees Celsius, and we have to put all these things in absolute temperature scales. Otherwise, it won't work. And as you can see, I set up the actual temperature ratio of the actual temperature to the standard temperature in such a way that it'll increase the volume occupied by 1 gram mole of the gas. So that's the way we would expect it to happen. As the temperature goes up, we'd expect it to occupy more volume. We don't actually have to correct for pressure in this case because it's coming in at 1 atmosphere. And so if we multiply all this out, we find that the molar flow rate of air coming in is 2.0449 moles per minute. Okay, so now let's just go to a new page. Now what we want to do is mole balance. And the general equation is that accumulation equals in minus out plus generation minus consumption. But this is steady state and there's no reactions. So the final balance or accounting equation that's relevant for this system is in equals out. So we can do a total mole balance. Okay, and that's going to be the moles of CO2 coming in. Plus the moles of air, all in moles per minute. So we find that the moles of the gas coming in is 190.7 moles per minute. Then the final step to get the volumetric flow rate is to convert, kind of go backwards now. Now we're going to convert the moles per minute into liters per minute. So we know that we have 190.7059 moles per minute coming in, and we again use the ratiometric method. we start out with the fact that we know that if this were an ideal gas at standard conditions, 1 gram mole would occupy 22.4 liters. But it's coming out at 25 degrees Celsius, so we need to correct for the fact that it's at non-standard temperatures. Again, putting it in absolute temperature scale. We're putting the ratio of the actual to standard temperatures in a way that makes physical sense, so that the volume occupied by a mole of gas increases because the temperature is warmer than standard. And then the pressure, actually, we don't really have to worry about because it's at standard pressure. And if you multiply all this out, you find out that the volumetric flow rate is 4,663 liters per minute. And there's only one sig fig for this problem. So the final answer to this would be that the volumetric flow rate in the product stream is equal to 5,000 liters per minute. So that's a lot different than the 150 liters per minute that we would have gotten if we tried to say that volume is conserved and that we could just add the volumetric flow rates together. So what I would challenge you to do is to go ahead and solve this using the traditional PV equals nRT equation, where you have to look up R in the unit system you're using. And you should get the same answer. To convince yourself that this method really works. Okay, that's all for now. That's what we'll be talking about shortly in class. This is what you should practice. I strongly encourage you to become familiar with and efficient using this ratiometric method so that you get away from having to look up gas constants. It invariably leads to mistakes. It takes longer, and by using the ratiometric method, you're actually thinking through what's happening in the process in a much more physical way. You'll be more in tune with what the problem is asking. You're going to solve for this part of the problem more quickly, and you're going to be much less likely to make mistakes.